Welcome to this explainer. Today, we're doing something really cool. We are connecting the deepest, most chaotic forces on our planet directly to something a little closer to home: high-scoring geography exam strategies. Whether you're just fascinated by how the ground beneath our feet can literally tear itself apart, or you're a student looking to totally crush the syllabus on tectonic risk and resilience, you are in the exact right place. We're going to take these massive, complex geological processes and distill them into clear, actionable, and visual insights.
Okay, let's dive into this. Here is our roadmap for today. 1. The breaking crust. 2. Earthquake mechanics. 3. Living with seismic risk. And 4. Mastering the geography exam.
Starting with Section 1, the breaking crust. This is where physical geography really begins.
So before any catastrophic shaking even starts, the Earth's lithosphere, the crust, has to snap. And faults happen when the stress on the rock simply exceeds its strength. We can actually categorize this chaos into 3 main culprits. First up, normal faults. This is caused by tensional stress. The crust is literally being pulled apart at constructive boundaries, causing a block of rock to just drop downward. Think of the massive East African Rift Valley. Next, we've got reverse faults, which are driven by compressional stress at destructive boundaries. Here, the rock is pushed together so hard that it snaps and thrusts upward, building gigantic structures like the Himalayas. And finally, strike-slip faults. This is shear stress at conservative boundaries, where plates are sliding horizontally past one another. They get completely locked up for years, and then snap. They violently give way, which is exactly what we see at the San Andreas Fault.
To really anchor this in your mind, I've got to share this brilliant teacher's tip. We call it the hands-on analogy, and you can honestly do this right now. Put your hands together, palm to palm. Okay, for a normal fault, slide one hand straight down. That's tension pulling the crust apart. For a reverse fault, slide one hand up. That's compression pushing it together. And for a strike-slip fault, put your hands side by side, knuckles touching, and slide one forward and one backward. That's your shear stress. It's such a simple physical movement, but it perfectly mirrors the massive tectonic forces shaping our continents.
Moving right along to Section 2, earthquake mechanics. Let's talk about unleashing all that energy.
All right, so what exactly happens when all that stored-up elastic energy finally just gives way? When we talk about where an earthquake happens, people get these 2 terms confused all the time. The focus, or the hypocenter, is the exact point deep underground where the rock fractures and kinetic energy is first released. But the epicenter, that's the point on the Earth's surface directly above the focus. When you hear the news talking about the epicenter, they mean the spot on the surface where those shockwaves are usually felt the hardest.
Once that underground fracture happens, the energy shoots outward in waves. First to the scene are the P waves, or primary waves. They're the fastest, punching right through both solids and liquids. Next up are the S waves, which are a bit slower and can only travel through solid rock. But here is the critical part. The absolute last to arrive are the surface waves, your Love or Rayleigh waves. Even though they're the slowest of the bunch, they are by far the most destructive because they violently move the ground both laterally and vertically, completely tearing infrastructure apart.
Now, how do we actually measure all this chaos? Definitions absolutely matter here. The Richter scale measures magnitude, which is the exact physical energy released down at the focus. It's a logarithmic scale. That means a single whole number jump represents a 32-fold increase in energy. It's massive. On the flip side, the Mercalli scale measures intensity. This one is highly subjective, based strictly on human impact, the observed damage to people, buildings, and the environment. Because think about it, a super high-energy quake on the Richter scale might barely register on the Mercalli scale if it happens out in the middle of a totally empty desert. That brings us to Section 3, living with seismic risk, the human consequences.
You know, the focus in modern geography has really shifted lately. It's no longer just about memorizing what an earthquake is. It's about understanding how societies actually survive them. Because the initial shaking, that's rarely the only danger. Earthquakes trigger a devastating chain reaction of secondary hazards. We're talking massive tsunamis, sudden landslides, raging urban fires from snapped gas mains, and this terrifying phenomenon called liquefaction. And it's super important to note that shallow focus earthquakes, where way less energy gets absorbed by the Earth before hitting the surface, are incredibly dangerous for triggering these specific cascading disasters.
I actually want to pause on liquefaction for a second because it is such a wild, vivid process. Imagine a container filled with wet sand. If you shake it violently, the water gets forced up right between the sand particles. Suddenly, the friction holding the sand together is completely lost, and that solid ground temporarily behaves just like a liquid.
This is exactly why, during major tremors, entire multi-story buildings in highly developed places like San Francisco or Tokyo can stay perfectly intact structurally, yet simply sink right into the earth. The ground literally just gives up its ability to bear weight.
So how in the world do we engineer resilience against something with that much power? Well, we tackle it on 3 fronts. Structurally, we use physics. We put buildings on base isolators, use heavy steel cross-bracing, and incorporate flexible materials that sway with the quake rather than snapping. Non-structurally, we lean heavily on tech, things like early warning systems and automated gas shutoff valves to prevent those horrific secondary fires. And finally, social preparedness. This means really smart land use zoning, like keeping high-density neighborhoods off that liquefaction-prone cell we just talked about, and running constant public education campaigns, like the classic drop, cover, and hold-on drills.
So the crucial point really boils down to this simple, powerful equation. Human risk equals the hazard multiplied by vulnerability. We absolutely cannot control the hazard. The plates are going to move, the San Andreas fault is going to snap, the energy will be released. But we can dramatically lower our vulnerability through smart engineering, education, and geoliteracy.
And finally, Section 4, Mastering the Geography Exam. Let's talk strategy and synthesis.
If you're gearing up for a geography exam, this is where the rubber meets the road. Listen closely to this standard. Exam strategy is no longer about just knowing the content. The examiners, they aren't looking for isolated geological facts just dumped randomly onto a page. They want to see the art of the connected answer. They are looking for application, evaluation, and synthesis.
To pull that off, you've got to master what we call the Geographic Chain of Causation. Every top-tier answer moves through these 3 rhythmic steps. Step 1, identify the physical process. Step 2, identify the resulting structural change. And Step 3, explain the human consequence. For example, don't just write that a fault snapped. Explain how the specific magnitude of that physical quake dictated the building design required, which then ultimately determined the economic resilience of the city. Connect these ideas together using keywords like consequently or as a direct result.
You also need to completely nail the evaluation component. When an exam question asks to what extent, they are hunting for a balance sheet approach. First, describe the mitigation strategy. How do those base isolators actually work? Second, analyze it. Why is it so effective in a place like Tokyo? And crucially, Step 3, evaluate it. What are the limitations and costs? Is this technology just way too expensive for developing nations? A totally one-sided answer will always cap your marks. You have got to weigh the pros and cons.
Next up is your case study toolkit. Please don't just memorize generic data. Memorize highly applicable facts using the 5 Ws. Let's look at the 2010 Eyjafjallajökull eruption in Iceland as an example. What was the event? Where specifically did it happen? Why did it happen? Was it a constructive boundary or a hotspot? Who was impacted? Frame this around specific groups like local farmers or the global airline companies that were grounded. And when? What was the exact chronology of the management response? Having this template ensures you always have targeted evidence ready to fire off.
So, how do we actually build all of this into a solid essay structure? For those long-form answers, rely on the Peel method for every major paragraph. Point. State your main argument crystal clearly. Evidence. Back it up with a hard fact, a statistic, or map data, like referencing a specific OS map scale. Explanation. Really delve into the why and how of the process. And finally, link. Connect your point back to the broader question and the unifying strand of geoliteracy. Doing this creates a flawless, undeniably logical structure that examiners absolutely love to see.
Well, we have covered a ton today. Everything from the deep tectonic stresses tearing the lithosphere apart to the incredibly innovative ways humanity survives the shaking, all the way down to structuring a perfect essay. So, I'm going to leave you with this final thought and a bit of a challenge for your own prep. How will you apply the chain of causation to connect a physical landform to human resilience in your next exam? Try doing a marking challenge. Write out a cohesive narrative, grab a real marking scheme, and honestly grade your own clarity. Keep exploring, stay focused, and use these frameworks to completely conquer whatever your syllabus throws at you.